This is assignment 5.3. Let's go. So number 1, it says write an equation of the tangent line shown. So the function, the curvy part, is f of x equals negative x cubed plus 4. They give you a point. Whenever we're doing an equation of a line, which we are, I like to organize it with x, y, and the slope. So we're given that x is 1, y is 3, and I need to find the slope of that tangent line. Well, the slope of a tangent line is the derivative. So I'm going to take the derivative and then plug in the x coordinate to find the slope. So let me show you what I'm doing here. So I have the function. The derivative is what's going to give me the slope. I have a 0.13. So if I plug 1 in here, the slope is negative 3. So I have negative 3, x minus 1 plus 3. So there's the equation of a tangent line. So that was part A. Then in part B, it says use that to evaluate at 1.1. So use that to evaluate at 1.1. Where there's an x, plug in 1.1. So 1.1 take away 1 is just 0.1. This is negative 0.3, so this is 2.7. So the idea is you can use the tangent line as an estimate for a function value, if it's close to that point. Part C. Part C is find the actual value, I think, at f at 1.1, right? What's the actual value? So the actual value, just substitute into the function. So what we just did was called linearization. It's to use the tangent line to estimate. So if you find the exact value of 1.1 into here and used your calculator, you get, I'm cheating looking at the answer key, 2.669. So you get an idea that the tangent line is pretty darn close, right, to what the actual value is. And sometimes darn close enough is good enough. But that's the work we're doing. Can you find the equation of a tangent line and then use it to evaluate rather than the function itself? All right, number 2. In number 2, scroll down, it says, make a large copy of the graph on your own paper. All right. So that's the graph of y equals x squared. A simple parent parabola. And then you have the point 1, 1. And it says, draw the tangent line at 1, 1. Maybe I'll change colors just for fun. That's a pencil. I'll do a pencil. So this is what I have so far. So I drew that graph. Here's my tangent line. And then it says write an equation of that tangent line. Let me do that. So if I want an equation of that tangent line, x and y are 1. And the slope is the derivative at 1. So the derivative is 2x. So plug in 1 and you get 2 times 1. You get 2. So I know these values. So the equation of a tangent line would be 2x minus 1 plus 1. So both x and y are 1. The slope is 2 using the derivative and plugging 1 in. It's the next part here. Label part. It says label a point. Now label a point on your tangent line with an x coordinate of 0.9. So if I look for 0.9, it's below. So I did that. Use your equation of a tangent line to approximate 0.9. So I'm going to plug 0.9 into the line. So 0.9 take away 1 is negative 0.1. And 2 times negative 0.1 is negative 0.2. So 1 take away 0.2. So that's 0.8. And then part E says, label a point B on the parabola with an x. What is the actual value of it? So like on the parabola at 0.9, it's actually above it just a little bit. It's hard to tell because you have to draw it super big. But if you label one A and one B, notice B is going to be a little bit above A for that tangent line. So that means A would be an underestimate because it's a little bit below B. So for that one, just plug in 0.9. So if I go 0.9 squared, that's 0.81. So you can tell that 0.81 is just a little bit bigger. I mean, they're very close, obviously, right? Using the tangent line. That's why you can't really tell right here. The difference literally is 1/100th. So if it's 1/100th, the distance between B and A, there you go. But it is an underestimate, 0.8. It's below. The actual value is a little bit bigger than 0.8. That'd be a good idea to know. Use the same tangent line to approximate 0.6. So if I use 0.6 into the tangent line, I got 0.6 take away 1. So that's negative 0.4. So if I double that, it's negative 0.8 plus 1, so that's 0.2 I have. And if I actually plug 0.6 into the function, so if I square 0.6 squared, I get 3.6. And the question is, how accurate is it? It's not very accurate. So for 0.6, put in the tangent line, and I got 0.2. When I put 0.6 into the actual function, I got 3.6. So it's not very accurate. And why is it not very accurate? Is because the further you go away from the x value of the tangent point, the less accurate it'd be. So what was our tangent point? 1, 1. So the further you go away from positive 1, so 0.6 is getting further away, the less accurate it is. So 0.9 is close to 1. So as long as it's close to the tangent point, it's going to be fairly accurate. But the further you go away, it's not going to be that accurate. All right, number 3. In number 3, approximate the square root of 26 using the equation of a tangent line. You must choose your own equation and point, and the graph should help. So if I want to estimate root 26 using a tangent line, let's go through those steps. So if I wanted to do that, there it is. Start with the equation y equals root x, right? And we want to pick a point that's close to root 26. So at 25, the square root of 25 is close to root 26. And if that's the case, then y would equal 5. And I want to find the slope of the tangent line. So in other words, I need to find the derivative of that. So that would be 1/2 x to the negative 1/2. And then plug in the square root of 25 to get that value. So the square root of 25, or plug in 25 and then do the square root. Now the negative exponent means it's not just the square root of 25, which is 5. It's the negative exponent, so it's going to be the reciprocal. So the slope of it is going to be 1/10. So if I put that all together, the slope is 1/10. The x-coordinate and the y-coordinate. So we have that is the equation of the tangent line. So if I want to estimate the square root of 26, for this one, I would plug in 26 to estimate it. So it's not the square root of 26. Plug in the x value. So the actual x value is 26. That's what I'm going to plug in. So if I plug in 26, 26 take away 25 is 1. So it's just 5 and 1/10 as an estimate. Or you could say the estimate's 5.1. And there's your estimate. using calculus to estimate the value of the square root of 26. All right, number 4. In number 4, the graph of a function shown there, if the derivative at 3 is negative 9. So you don't even have the equation of that curve. All you have right now is a derivative and a point. But that's all we need to estimate with the tangent line. So the point on the graph is 3 and 30. So that's x and y. The slope is going to come from the derivative. And it says the derivative at 3 is negative 9. That means the slope is negative 9. And then I'm going to put this all together to write the equation of a tangent line. So we have negative 9, 3, and 30. So this is what the equation of the tangent line looks like. So you have the slope is negative 9. We go x and change the sign and then keep the sign for a linear equation. So there's our tangent line. The question is, what do you do with that tangent line? And you estimate 3.1. So we're going to go back here. So plug in 3.1 to estimate it. And the closer 3.1 is, or the closer the number is to 3, the more accurate the estimate is. So 3.1 take away 3 is 0.1. Negative 9 times 0.1 is negative 0.9. So if I put this together, I get 29.1. Number 5. In number 5, it says find the actual value of 3.1 from problem 4, or explain why it can't be found. So I just told you it can't be found. So the actual value cannot be found because no function has been defined. So you know a point and you know the slope at a point, but the actual value cannot be found because no function has been defined there. So you're given a graph, but you're not told what the exact function value is or what the relationship is there. So you're given as a point and a slope at a point, but that's it. So there's no way to find the actual value without using the tangent line to approximate what the value is. Number 6. In number 6, you have a point 5, 2. So I'm going to write down x is 5 and y is 20. And you're given an equation, x times the square root of x squared minus 9. It said use the tangent line to approximate the y coordinate when x is 5 and 1/5. So let's go through the work for that. So this is what I'm trying to get to. What the value is at 5 and 1/5 using the tangent line. Now, I need to take the derivative here to find the slope. It's going to be the product rule. So that's the first times the derivative of the second plus the second times the derivative of the first. Now, I don't really need the 1 there, but I put it there. So there's the derivative. If I want to, I then need to, wherever there's an x, to plug in 5 to find the derivative at that x value. So 5, 25, take away 5 squared is 25. All right, so let's work through that. So wherever there's an x, plug in 5 and simplify it. So I got 5 over 2. Here I got 16. Now the square root of 16 is 4, but it's the reciprocal. Again here, 25 take away 9 is 16, and the square root of 16 is 4. So I'm going to put this together. I need common denominators for the next part. So I'm going to multiply by 8. So that I have 37 over 8. So there's the slope, 37 over 8. Did I do that right? Let me see. Oh, you know what I forgot? I know what I forgot. Is right here, I forgot the hook. There's a hook 2x. That's what I forgot. Did any of you do that? And say, hey, there's a chain rule. There's a chain that you forgot. So right here, there's a chain of 2 times 5. So 2 times 5 is 10. That's what I forgot, is the 10. So if I put this together now, I have actually 50 over 8. And so 50 over 8 would be 82 over 8. And if I reduce that down, it would be 41 over 4. All right, now I'm on track. So the slope is 41 over 4. So the equation of the tangent line is 41 over 4, x minus 5 plus 20. That's the equation of the tangent line. Now use that to approximate 5 1/5. So put in 5 1/5. So that's 41 over 4. 5 1/5, take away 5, just leave me with 1/5. So if I multiply it, it's 41 over 20. I need common denominator, so I multiply top and bottom times 20. And so you have your answer. So there's the approximate answer, using a tangent line to do an estimate rather than the actual function. All right, on to number 7. So those are all work with tangent lines. Now I think is review questions, which is great. So the length of one side of a square is found to be 8 inches with a possible measurement error of a 1/16 of an inch. Instead of using the actual area formula, approximate the area of the square using a local linearization of the area formula if the length of the side is really 8 1/16. So to do this, we're going to create a tangent line out of this. So how do I create a tangent line? So the length is really 8 1/6. So I'm going to pick one that's close. So I'm going to use 8 because it's close. So if S is 8, then the area is 64. And then I want to find the derivative. So I'm going to pick a number close to 8 1/16. So I'm going to pick 8. So I have 8 and 64. Because 8 is close to 8 1/16, and using that to approximate. And I want the equation of a tangent line, so I need to know the slope there. So in essence, let me show you my work here. In essence, if the side is 8, that's like x. If the area is 64, that's like y. And then I want to find the slope, which is to find the derivative at 8. So we have a equals s squared, so the derivative of that is 2s. And if I plug in that value 8, then the slope is 16. So I plugged in 8 into here, 2 times 8, 16. So as a tangent line, you still go y equals. So it'd be y equals, slope is 16, x minus 8 plus 64. Now I have the tangent line. So what am I approximating with that? Was 8 and what, 1/16? Yes. So 8 and 1/16. So then plug that in to find the estimate of it. So if I plug in 8 and 1/16 and subtract, I'm just left with 1/16. Notice the 16s divide out and you get the answer 65. I don't know if I have a unit involved there. Do I have a unit there? Inch. So that would be 65 inches squared. So the approximate area of that would be 65 inches squared. Now, if there's an error of 1/16, it could be actually less than that. So if there's an error of 1/16, it could be more than 1/16 or less than 1/16. So part B is, what happens if it's less than that? So take the same thing. This time it's 7 and 15 over 16 that we're doing for part B. So now the error is the other way. If I substitute in here and subtract, I end up with negative 1/16. So then it's 63 inches squared. So you have this and this, right? So if I plug in 7 and 15 over 16 here and subtract 8, I get negative 1/16. The 16s divide out, and there I go, 63. Then part C says, so use your answers to find an approximate range of values. So this was A and B, so the range of values go from the low 63 to the high 65. So if there was a range of error here, and this is at what, inches squared. So you had a range of error of 1/16 of an inch. How does that affect the area? So if you know there could be an error bigger than 1/16 or less than 1/16, then the range of possibilities would be all areas from 63 to 65. Completely engineering type stuff that we're talking about here. All right, number 8. Use a tangent line to approximate 8.01 if f at x equals the cube root of x. So f at x equals the cube root of x. We need and our goal is 8.01 without plugging in 8.01 and not having a calculator. So how does the tangent line help us estimate that value? So I need a number close to 8.01 that I actually know the y value of. So that would be 8. And the cube root of 8 is 2, and then the slope. So to find the slope, I take the derivative. So I want the derivative of the cube root of x. Now remember, this is just x to the third. So if it's x to the 1/3, then the derivative is 1/3 x, and subtract 1 from the exponent. That's the derivative. So again, this means x to the 1/3. They're the same. So 1/3 times 1, and then subtract 1. So 1/3 take away 1 is negative 2/3. Then plug in 8 to get your slope. So I want to figure out the derivative at 8 to find the slope. So that's 1/3, 8 to the negative 2/3. So if I did that, understand the cube root of 8 is 2. The cube root of 8 is 2, and 2 squared is 4. But the negative exponent makes it 1/4. So if I multiply it together, I get 1/12 by multiplying the tops and bottoms. So the slope here is 1/12. So now the equation of the tangent line is 1/12, and it's x subtract 8 plus 2. And now I can use 8.01. So now use 8.01. And so that's 0.01. It's a little bit complicated when one's a decimal and one's a fraction. So I would change 0.01 to 1 over 100. So if I multiply this across 12 times 100, it's really 1, like it's 1 over 1200. Make sure how my answer key looks at that. So you have your answer. That's correct. Yay. All right. Number 9. All right. These are review questions. I'm just going to keep going through for this. See how far I get. All right. The point 1, 2 is on the graph x cubed plus xy plus y to the 4th equals 19. Well, this is not review yet. Use the equation of a tangent line to approximate 1.1. All right. So to do an equation of a tangent line, I have my x and y value. I need to take the derivative here. So let's do that. That's 3x squared. This is the product rule. So the first times the derivative of the second times the derivative of the first. So the derivative of x is 1, so I don't need it. And then the derivative of y to the 4th, but it needs the hook y prime. And the derivative of any constant is 0. Now I'm going to gather together the y primes. And if it doesn't have a y prime, I'm going to subtract it or add it to the other side. So in this case, I'm subtracting the 3x squared and the y to the other side. I'm going to factor out a y prime. And then divide. So there you go. Negative 3x squared, subtract y, divide, and that's what you get. Now, I have a point, so I want to find the derivative at that point, 1, 2. So where there's an x, plug in 1. And where there's a y, plug in 2. So that's negative 5. This is what, 33? So it's negative 5 over 33. Now put it all together. So there's the slope, negative 5 over 33. X is 1, y is 2. So that's the information I need. So the equation of the tangent line is negative 5 over 33, x minus 1 plus 2. So there's the equation of the tangent line. Use that to estimate 1.1. So I'm going to use that to estimate 1.1. So 1.1 take away 1 is 0.1. That's the same as 1/10. So negative 5 over 33. Let's finish this off here, over here. So it's negative 5 over 330 plus 2. Common denominators, that's negative 5 and 660. Here, I'll do it here. Negative 5 and 660. Right? So that's 555 over 330. I don't even care to reduce it down. And you know what? As long as it's numerically equivalent, it doesn't matter. Like, for instance, exactly at this point, if it was an AP exam, you would quit. So as soon as you plug it in and it's numerically equivalent, you get no brownie points for just keep going on and on. You can only get it wrong after that if it was free response. If it was multiple choice, you might have to work to get the answer. But for this, if it was free response, you would leave it that way as a linearization and not simplify it. Number 10. Use a calculator to find the actual value when x equals 1.1 and then show the equation that you're solving. So wherever there's an x, put in 1.1. So wherever there's an x, put in 1.1 and then use your calculator. This is what it would look like. So I'll show you. So wherever there's an x, put in 1.1 and then use your calculator to solve that equation. So to solve that equation, you go menu algebra and then you go solve, and it's parentheses 1.1 cubed plus y, or it's 1.1y, plus y to the fourth equals 19, comma y. And then you have your solutions. There are actually two solutions to this. So 1.1 cubed plus 1.1y plus y to the fourth equals 19. Now for this one, it gives you two solutions. But really, what was the solution we found with the tangent line? What was it close to? So it was actually the positive answer, right? 1.984, because it was a positive number. So the approximate answer, the exact answer with your, or using your calculator, that's what you get. And if you took the fraction, you get a similar answer. So the fraction you got on the last one, this 555 divided by, what is it, 330? That gives you like almost the same answer. Okay. Number 11. What's number 11? All right, this will be our last one for this video. Given the function y equals x cubed, use the equation of a tangent line to approximate 2 1/6 to the cubed without using a calculator. So to do that, I need a number close to 2 1/6. So I'm going to pick 2. And if x is 2, then y is 8. And now I need to find the slope. So I need to take the derivative and then plug the x value into the derivative and then come up with the equation of a line. I wonder if you can try that. I'll show you my work in a moment. Can you do that? 2, 8, and then take the derivative and then plug the x value in, which is 2, to find the slope, and then put it all together. So let me show you my work. So did you get something like that, where you used 2 and 8 and then took the derivative and then plugged 2 into the derivative, and now you have the slope and 2 points in the equation of line. Now I want to approximate, oops, I didn't mean the calculator. I want to approximate 2 1/6. So if I approximate 2 1/6, that's what it would look like. So again, if I approximated 2 1/6, that's what it would look like. So it'd be 12. 2 1/6 take away 2, it just leaves me with 1/6. And then 6 goes into 12 twice. So altogether, 2 plus 8 is that. So to approximate, what's the value of 2 1/6 cubed? We use the tangent line instead of going 2 1/6 times 2 1/6 times 2 1/6. Here's a calculus way to be able to estimate what that value is. So I was trying to estimate the value of 2 1/6 cubed. And the approximate value of 2 1/6 cubed is 10, using the equation of a tangent line, where we took an x value very close to 2 1/6, and then the y coordinate that goes with it, created a tangent line out of that, and the slope of the tangent line from the derivative. And then we use the tangent line instead to find that approximate value, instead of going 2 1/6 times 2 1/6 times 2 1/6. All right, Mr. G Math over and out. I'm proud of you for doing your work. And that was part 1, and I'll see you for part 2.